also want to do that. Share screen. And just right on my screen.
All right, nice.
Now I gotta figure out what I'll listen.
Cool.
Because they changed some things.
Am I supposed to do this when I teach the class?
No,
I'm an old guy.
this is just my,
This is so fancy. It's way
I-
above my.
I also record my videos
Oh
still,
yeah.
and that way they still have them.
All right. Just let them know that we're gonna do a parkour. Unfortunately.
Why are you doing this, Claire?
Okay, folks. Let's go ahead and get started. I will start with several announcements. And then go from there. The very first thing I wanted to do is make note that tomorrow, the lab for tomorrow is going to be related to the change in boiling point. So in other words, what we were discussing on Friday and the previous Wednesday. Make sure that your pre-lab is printed on a separate sheet because you will be turning it in and it will be graded this time. Last time I gave you 5 points for just doing it. This time it's actually going to be graded and it will be turned in when you come into lab. So make sure it prints on a separate sheet. Forgot something. Number 2, I am going to give you a copy of what you're going to get in addition to the exam tomorrow. So in other words, the formula sheet and all of that jazz. So you will see exactly what you're going to get and know what you need to have memorized for the test. Yes, did I say? Oh, apparently I was looking at that this Friday. Sorry. No exam tomorrow, that was just too loud. So as you can see, you are given the Clausius-Clapeyron equation. You are given the R value, the ideal gas constant in joules. You are given the equations you need for the heating and cooling curve. You are given your concentration formulas. You are given the freezing point depression and boiling point elevation calculation with both the Van Hoff factor included or not included, but basically I always use the one with the Van Hoff factor. And you're given the colligative property pressure calculation. You're also given the solubility rules. The reason for the solubility rules is so that you know what you need to do about the Van Hoff factor. Because if it's soluble, that means you got to let it dissociate. And therefore multiply it by the appropriate number of particles in solution. I also give you a copy of the periodic table, and then the last periodic table, if you watch my videos, you'll see that I tend to determine polarity based off of the electronegativities. I gave you a table of electronegativities. Whether you use all of this stuff or not, that's up to you. But you have all of this stuff. Now, I have written the exam. And now I'm going to do it strictly from memory because I forgot to bring a copy of it with me. You have four, I want to say it's four, it may be three, molecules where you have to determine the intermolecular force or forces that are present. You have two where you are given two different compounds and you have to choose either highest boiling point, lowest boiling point, highest melting point, lowest boiling point type of concept. You circle the correct, the ones. You have a question, again, where you're given two different compounds to choose between, and you have to determine viscosity. There is a short answer question where I'm going to see how well I can read your writing, where you actually have to explain a molecule's behavior with respect to its vapor pressure. There's a series of questions about how to increase or decrease the solubility of a gas or ionic solid. There is a heating and cooling curve. There is a Clausius-Clapeyron equation. There is a series of questions related to phase diagrams, or a phase diagram. There's a set of questions basically asking you to determine if a solution will form, may form, or will not form based on solute-solvent interactions compared to solute and solvent interactions. There's a series of, think of 5 questions where you have to interpret a solubility diagram. Basically, this is the saturated, supersaturated, unsaturated stuff. There is a either freezing point or boiling point calculation to perform, colligative property, and there is a pressure calculation to perform, colligative property. And there is a single concentration conversion. In other words, the test is fairly thorough over what we've covered. Questions? Yes. Okay, so I was just asked, I said one was open-ended, are the rest multiple choice? The math questions are not multiple choice, they are also open-ended. That way I can give partial credit. Which I should say, show your work. Because I do give partial credit. But if you don't show your work, you don't get it. If you miss it. Other questions? What I just gave you, all the formulas and stuff, that is provided on the test. Basically, you'll remove the last 2 pages of the exam. And it'll be exactly what I just gave you. From now on, I won't be giving out what I'm gonna give you, but this gives you an idea of what I do. So pretty much I give you all your formulas, I give you all your constants. I will say on the concentration calculations, I did give you your molar masses so that you're not having to take time doing the molar mass. So I try to make it, I mean, it's thorough, but I try to give you a lot of stuff too. Other questions? Okay. So then I am going to get into today's information. We're going to start with an example similar to what we were ended with on Friday. And I don't know why my pen is doing weird, funky things. I guess I don't pick it up far enough. Okay. So for the reaction 2A plus B goes to form 3C, write an expression for the rate in terms of the change in concentration of reactants and products. If you'll recall, basically, the rate is going to be related to the change, to the loss of reactants, and the rate is going to be related to the gain in products. We represent the loss with a negative value. And so for our reactant A, it would be the loss would be in terms of change in A, of concentration of A versus a change in time. For B, it would be the change in concentration of B versus a change in time. And for C, it would be a positive change in C versus a concentrate or change in time. Now, to make A equal to B equal to C, we have to take into account the coefficients. And we do so by, it's 1 over the coefficient of that particular material. So 1/2 for our A. That would make that equal to 1/1 for the B. And that would make it equal to 1/3 times the change in C over the change in time. So again, we use those coefficients in order to make all of the concentrations equivalent, A, B, and C. Okay, so when A is decreasing, at a rate of 0.200 molar per second, how fast is B decreasing and C increasing? Okay, to make this where we have B, we're going to simply put these, the A and the B, equivalent to one another. So it would be a -1/2 the change in concentration of A over the change in time is equal to the negative of the change in B concentration over the change in time. Now, it was specified that A was decreasing, meaning it's a negative, it's going away. So the negative, it would be a negative change in concentration because the change, delta, the change in is always final minus initial. So if it's final minus initial and it's going away, that means the final has to be lower than the initial. So it would be -1/2 of a negative to 0.200 molar per second is equal to a negative change in the concentration of B over the change in time. Or in other words, we're looking at 0.100 molar per second is equal to the negative of the delta B over the change in time So we're looking at a loss of 0.100 molar per second for our concentration MB over a change in time. Again, the negative does not mean negative because you can't have a negative concentration. The lowest you can go is 0. All negative means is which direction is it heading. Now, for the other half of this question, it asked for C. So we're going to be using those two parts of the equation. So for the other part, it's a -1/2 change in A concentration over a change in time is equal to 1/3 the change in concentration of C over the change in time. So it would be a -3/2 of a -0.200 molar per second would be equal to our change in C over change in time. So it'd be 0.300 molar per second would be our change in C concentration over a change in time. If I did this correctly in my head. Yeah.
I have a question.
Yes.
Did you cross multiply the 1/2 or did you multiply one of those by 3?
Multiplied both sides of the equation by 3 in order for them to cancel out. Questions about if you developing the rate of reaction based off of the reaction itself. Yes. It is because back in this conversation or back in the thing, it said A is decreasing. So that means it's going away. So it had to be negative. Yes.
So for calculating how fast C was increasing, you don't need it all.
No, because this equality up here, you can take any part of the equality and put it together. So I can use A and B like I did the first one, or I can use A and C, or if I'd have known B, I could have done B and C. So you only need 2 parts of the equality.
I'd argue using B would have been easier.
Well, the fact is maybe using B would have been easier, except we weren't given B's information. And it's always better to start with the information you were given so you have less chance of calculation errors. In case I made a mistake the first time, I wouldn't have propagated the mistake. Other questions? Okay, it seems nebulous right now a little bit. Other than what does rate mean? It means what concentration of reactants is going away over a given amount of time, or what amount of products is being formed over a given amount of time. That's what rate means. But how do we get these numbers? How do we come up with this stuff? These numbers to begin with? That's where experimentation comes into play. And so that's where we're headed with this information, is into the experimentation side. And we're going to be looking at two different types of experiments that will allow us to calculate the rate of the reaction, or allow us to determine the rate of the reaction. But before we get into using those calculations, the first thing we've got to discuss is the general formula of what is produced. So let me recap that statement. These rates of reactions have to be determined experimentally. They cannot be determined using numbers out of a textbook. They have to be determined experimentally. There are two methods that we use to determine this information experimentally. Those methods are the method of initial rates and integrated rate laws. That's how we're going to determine this information experimentally, is using one of these two methodologies. Now, what is produced from this information is a rate law. All rate laws have a general formula. They are equal to, so if I have a reaction, A goes to B, then the rate law is going to be rate for the reaction is equal to K, lowercase k at that, times the concentration of A raised to a power. This lowercase k is called the rate constant. And the power is called the order. If I have A plus B goes to form C plus D, then the rate law is going to be rate is equal to the rate constant times A raised to some power times B raised to some power. Again, the lowercase k is our rate constant. And in this case, the X and the Y are the orders. Now I'm using X and Y, but when you look at the homework, I used X and Z. They're just variables. It can be it's just a variable, X and Y. Now, what's one thing, let's talk about some things that you may or may not notice when we deal with a rate law. The only thing that goes into the rate law are the reactants. So up here, A was my only reactant. It was the only thing in the rate law. Here, A and B were reactants, so they're the only things in the rate law. Second thing you will notice is that the right-hand side of this equation is all multiplication. So it's the rate constant times the concentration of A raised to its order times the concentration of B raised to its order. Now, another piece of terminology we're going to use is going to be the overall order. And basically the overall order for this second one would be X plus Y is equal to the overall order. So in other words, you simply add the superscripts together to get the overall order. Okay. So the rate of our reaction is equal to the rate constant for that reaction times the reactants collisions. If those reactants do not collide, you're not going to have a reaction. So when we're describing this overall order, what you're actually describing it describes how many of each molecule collides to cause the reaction. The order and the overall order are not based on stoichiometry. When we write a rate law, the order is not based off of the coefficients. The only way to determine the order is experimentally. So there's a lot of key pieces of information that I just went over. The rate laws are going to allow us to determine the rates. They're going to allow us to determine the rate constant. They're going to allow us to determine a lot of other pieces of information. The only way to get to those rate laws is through experimentation, either using the method of initial rates or the integrated rate laws. When we develop a rate law, it always is going to have the same generic form. It's going to be rate is equal to the rate constant times the concentration of the reactant raised to its order. The order describes how many of that molecule actually participates in the reaction. So let's look at some examples of rate laws. So NO2 reacts with carbon monoxide to form nitrogen monoxide and carbon dioxide. Experimentally, the rate law for this reaction was determined as rate is equal to K times the concentration of NO2, technically raised to the 1, but we often do not illustrate a 1. I don't care if you do or not, but oftentimes we don't illustrate the 1. What this means is, regarding this reaction, carbon monoxide has no impact on the speed of this reaction. The only thing that impacts the speed of this reaction is how fast NO2 dissociates. That's what this means, is that since nitrogen dioxide was the only thing in this rate law, everything is dependent upon the nitrogen dioxide. Carbon monoxide does not play a role in that reaction, not in the speed of the reaction. Now, once nitrogen dioxide does its thing of dissociating, then that carbon monoxide comes in and plays a role in the reaction. But as far as in the speed of the reaction, which is what we're talking about, it is only dependent upon the nitrogen dioxide. Let's look at another example. 2NO2Cl goes to form 2NO2 plus Cl2. This has a rate is equal to K times NO2Cl. Even though there's a 2 here as the coefficient, notice that the order is not reflective of that coefficient. The fact of the matter is, it depends upon only one of those NO2Cls reacting to start the reaction. Yes, once it started, it goes. But we're talking about what does it take to get the reaction going? What is the rate determining step in the process. Let's look at another one. 2NO plus 2H2 goes to form 2N2 plus 2H2O. This has a rate law. Rate is equal to K times NO squared times H2. First of all, the overall order would be 2 plus 1, or in other words, it is 3. The speed of this reaction is based off of 3 molecules. 2 nitrogen monoxides reacting with hydrogen. Now, folks, this is all based on collision theory. In order for this reaction to occur, the nitrogen monoxides, 2 of them, and the hydrogen have to collide with perfect symmetry at the same time with the right amount of energy. If they don't collide with the correct symmetry, with the correct energy at the right time, then the reaction doesn't occur. Now, it's hard for a reaction to get going if it's based off of 1 molecule, like in this first one and in the second one. 2 is probably ideal. 3, you're getting to the maximum. You very rarely are going to see anything that has a order of 4 or more, because it would be hard for 4 molecules to react simultaneously with the correct energy, with the correct orientation at the same time, all of that jazz. So 1 means that it is separating on its own. 1 means that it, or 2 means that you've got 2 molecules hitting each other, which is probably ideal. 3, you're at max, typically, with very few experiments allowing for 4 more. Something else about these orders, though. Orders can be whole numbers, fractions, and negative numbers. And it's all describing what's going on, how it participates. Okay. I didn't get to method of initial rates, and that's going to take me some time. So instead of holding you for 5 more minutes, I'm going to go ahead and let you go 5 minutes early, and we're just going to deal with method of initial rates on Wednesday. Because they take time, yes. A negative number would indicate that it has, when we actually get into the rate law, it means that it's in the denominator. rather than in the numerator, it means that it can negatively impact because it divides it. It doesn't help. It actually causes resistance. By the way, I will be available via email today, but after 2, I may or may not be available at all.